We've been looking at the nervous system as this rather neat sorting machine, passively cataloging incoming signals. But let's be real, that's not quite the whole story, is it? The organism isn't just a passive recipient, it's actively living, breathing, responding. This chapter pushes us to think about how the nervous system, embedded within this living, active body, actually makes sense of the world and decides what to do about it. We're moving beyond just recording the environment to understanding the organism's unique relationship with it. Now, remember the behaviorist craze. All that observable action, stimulus, response, black box approaches. It was useful, sure, but it kinda sidelined the brain's fancy central processing units. It was like studying an orchestra by only watching the drummer. What we're doing here is deliberately flipping that script. We're zooming in on what happens inside, focusing solely on how sensory impulses get reprocessed centrally. Think of it as ignoring everything else for a moment to really appreciate the complexity of the central command. We're treating the nervous system less like a lone archivist and more like a sophisticated control tower managing a bustling, complex city, the organism itself. And honestly, we're standing on the shoulders of giants here, building on all that amazing research done over the last generation. Okay, so this control tower isn't just one big room. It's got levels, right? A hierarchy. From basic reflexes happening way down low in the spinal cord to the super complex stuff happening up high in the cortex. And when we talk about connections, there's this interesting tension between what we inherit versus what we learn. Like, some wiring is probably baked in from evolution, while other pathways are forged through experience. Though, spoiler alert, the text admits we're still fuzzy on exactly how much is which. Crucially, it's not just a one-way street. Sensory input drives action, yes, but the actions we take also feed back information, shaping how we perceive things next time. Think about how knowing you've moved your arm changes where you feel a touch. That's proprioception talking, and it's key, along with signals from inside the body, telling us about our internal state, our needs, our drives. Let's rewind a bit. Why bother with all this complexity? Well, survival, plain and simple. Organisms need to adjust to maintain balance, homeostasis as Cannon called it. Even the earliest life forms had to react differently to different nudges from the outside world. Now, this isn't just cause and effect, it's about discrimination. Responding appropriately to keep the lights on, so to speak. And learning plays a role too, though it's distinct from evolution selecting for traits. The text makes a crucial point. Figuring out how the body adjusts itself internally, how it maintains its own existence, comes before tackling the big question of intentional behavior towards external objects. It's like mastering your own housekeeping before you start building a spaceship. Concepts like von Bertalanffy's open systems help frame this internal balancing act. So evolution gives us fancy receptors, eyes for light, ears for sound, taste buds for chemicals. Great! But having a specialized receptor doesn't automatically mean we experience a distinct quality, like the difference between seeing red and blue. That's a leap. Alongside developing these receptors, organisms also develop specific ways to move or react to those stimuli. Imagine having a light sensor but only one possible reaction, twitch. Even if you have sensors for many different things, if your reactions are limited, you don't get a rich tapestry of sensory experience. The real magic, the essence of these qualities, is that a single stimulus doesn't have a fixed meaning. Its significance shifts depending on the company it keeps, what other signals are coming in, both from the outside world and from within the body. Context is king. This contextual meaning has huge implications. If the same signal can mean different things depending on the situation, then the raw signal arriving at the brain can't just trigger a preset response. It needs to be evaluated, weighed against other information coming in at the same time. Think of it like receiving a text message. Meeting at 3. Alone, it's vague. But if you know you're at work, it means something very specific. Similarly, a sensory impulse needs to be integrated with other signals before the final decision about the response is made. Simple reflexes exist, sure, but they're just the tip of the iceberg. Even those quick reactions send feedback signals upwards, basically saying, "Hey, I got that stimulus and I did this." This feedback starts marking the original signal with potential implications for action. And this integration process isn't just a one-off deal. It's like a relay race. The initial signal hits the first station, say, the spinal cord. It triggers a response, sends feedback, and passes the baton, along with other incoming signals and reports from lower levels, up to the next station, maybe the brainstem. Then the thalamus gets the package, adds its own reports and feedback, and sends it onward. Each level gets a richer, more complete picture, incorporating not just the original external signal, but also the history of responses and other relevant information. Why bother with all this complexity? Because once you have specialized responses for specialized stimuli, you need a way to coordinate them. If seeing a snake triggers a freeze response, but seeing a mouse nearby triggers a run response, the system needs to handle these conflicting signals based on their combination. Now, don't imagine a strict line between a simple reflex and a conscious decision. Reality is messy and continuous. Most of our actions fall somewhere in between. Just as we bundle similar sensory signals together to create perceptions, we also bundle motor commands together to produce coordinated behaviors. Think about walking. It's not just one muscle contracting, it's a whole symphony of muscles firing in sequence. These complex movement patterns are likely triggered by relatively simple signals from higher centers. It's like giving a high-level command like "go fetch the ball" instead of specifying every single muscle twitch. And just like perception requires more than one nerve fiber firing, producing a smooth, precise movement probably requires the coordinated firing of many motor neurons, not just adding up individual muscle twitches. Let's ditch the simplistic single neuron in, single neuron out reflex model for a second. It's probably too neat. Instead, there's a whole spectrum of connections. At the simplest end of this spectrum, we have classification. Imagine a group of slightly different touch sensations, maybe varying intensities or locations. If they all trigger the exact same motor response, say, pulling your hand away, that's basic classification. Any member of that group gets mapped to the same action. This is exactly what we see in conditioned reflexes and generalization. Pavlov's dog salivating to the bell and then maybe also to a similar tone. The brain groups similar inputs and links them to the same output. It's the first step towards creating order from raw sensory data. We can take this classification game up a notch. Instead of just one possible response for a group of stimuli, what if we connect several different responses? Which one gets executed then depends entirely on the context, on what other signals are buzzing around at the same time. This is getting closer to flexible behavior. Down at the lower levels, this kind of selection might be pretty basic. Maybe the frog can tell the acid is on its back and initiate a leg kick, but that's probably only effective for that specific kick and that specific location. It's detailed for that task, but very narrow in scope. As we move up the hierarchy, though, the potential for more complex connections increases, allowing for decisions based on a wider array of inputs and potential actions. Here's where things get really interesting, especially concerning proprioception. Remember those feedback signals traveling up? They carry news not just about the external world, but about the body's own reactions. So the signal reaching the higher brain centers isn't just bright light detected. It's bright light detected, and pupil constricted and head turned slightly. The organism's spontaneous reaction becomes part of the ongoing environmental report for the higher centers. It's like the car driver not just seeing the red light, but also feeling the brake pedal engage. And crucially, it's the feedback signal, the report of the movement, that matters for further processing, not the movement itself or the original motor command. This is a key point against overly simplistic behaviorist views focusing only on the observable action. So behavior isn't just an output, it's also an input. Our actions shape the very information we receive next. Those automatic, lower-level responses help build the foundation of the sensory stream that flows upwards. And then the higher centers, using this richer, context-aware stream, guide the more directed actions. Think about driving again. You see the car swerving, you hear the screech, and immediately you expect the car to swerve, maybe brake. Those observed events become meaningful signals predicting the vehicle's response. Similarly, the higher brain uses the integrated stream of sensory and proprioceptive feedback to steer the ship of the organism through the world. This role of the higher centers is nicely captured by the analogy of a military commander. The commander knows their troops will react automatically to certain situations. Sometimes, the commander figures out what's happening not by direct observation, but by seeing how the troops react. Seeing smoke rising might tell the commander there's a fire, even if the flames aren't visible yet. The commander only steps in to override standard procedures when they know something the troops don't, like a hidden minefield. Similarly, the higher brain issues general directives, like navigate towards food, while the lower levels handle the specifics of steering, avoiding obstacles, adjusting speed based on the immediate sensory feedback. This interplay gets even deeper. Some movements are practically part of perception itself. Think about how focusing your eyes involves subtle movements and gives you kinesthetic feedback, or how crossing your fingers changes where you feel a touch. Von Weizsäcker talked about a complete entanglement of Verflechtung, of sensation and movement. It's not just that movement affects perception. Perception constantly informs and shapes our posture and readiness for movement. Stretching your arm out means you're expecting to interact with something ahead. Conversely, the feeling of your arm being raised carries the expectation of reaching. It's a two-way street. Individual nerve impulses might be ambiguous on their own, gaining meaning only when considered alongside the whole pattern of simultaneous signals. Just like sensory signals get bundled into perceptions, motor signals get bundled into coordinated actions. A complex behavior, like catching a ball, isn't just a random sequence of muscle contractions. It's likely evoked as a whole pattern by a relatively simple signal from a higher center. Think of it as issuing a command, like catch the ball. The lower levels then figure out the exact how to do it, coordinating the timing, force, and trajectory based on ongoing sensory feedback, especially from proprioceptors. So, the higher centers issue general directives, selecting a class of behaviors appropriate for the goal, and the lower levels handle the execution and fine-tuning within that class. Now, don't assume that innate behaviors are rigid and learned ones are flexible. It's not always that simple. An inherited reflex might be incredibly adaptable to changing conditions, while a learned skill, after lots of practice, could become almost automatic, running on autopilot at lower levels. Some complex behaviors might be innate but handled by higher centers, while others are learned but executed lower down. Selecting and carrying out a behavior isn't a single event, it's a dynamic process involving multiple stages and factors. And crucially, feedback is the lifeblood of this process. As you start moving, you get constant streams of information comparing what you expect to happen with what is actually happening. This allows for real-time adjustments, corrections, ensuring the behavior achieves its goal. Okay, we've talked a lot about adapting to the external world, but what about adapting to the internal world? Why do we behave differently at different times, even in the same environment? Because we have needs. Hunger, thirst, fatigue, these biogenic needs arise from our internal physiology. These aren't just passive states, they actively shape our behavior, creating a disposition towards certain actions. Being hungry makes you disposed to seek food. Being afraid makes you disposed to flee or fight. These internal drives are deeply intertwined with emotions and motivations. They give certain external stimuli a special subjective value. Food looks particularly appealing when you're hungry, and danger feels especially threatening when you're scared. Alongside these basic needs, we have emotions: fear, joy, anger. These are another type of disposition, often triggered by complex social or environmental situations. Like needs, they predispose us towards certain actions and color how we perceive and respond to the world. We can think of emotions as affective qualities, forming their own subsystem within the larger mental order, much like vision and hearing form subsystems within the sensory order. A key difference is that affective qualities relate to a global feeling about a period of time, not specific spatial features. But fundamentally, They operate similarly. Similar emotions evoke similar subsequent neural responses, making them functionally equivalent within the system. Interestingly, the way the text describes the emergence of these affective qualities bears a strong resemblance to the James Lange theory of emotion. The idea that bodily changes contribute to our emotional experience echoes the role of proprioception in spatial perception. However, the text cautions against a simple reductionist approach. Saying emotions are just bodily sensations is like saying vision is just retinal signals. It doesn't fully explain the quality of the experience. If you try to reduce all mental qualities down to relations between basic elements, you end up replacing the rich tapestry of experiences with a complex web of relationships that looks just like the original tapestry. It doesn't solve the mystery of why we have these distinct qualities in the first place. So, we've journeyed through how the nervous system takes raw sensory input and starts organizing it, creating these structured qualities. We've seen the importance of context, feedback, hierarchy, and the interplay between innate and learned aspects. Now, we're poised to look at the bigger picture, how this entire mental order is structured. This next section will sketch out the general principles of this organization, keeping in mind that we're still dealing with broad outlines, not specific details for any particular creature. We'll continue to gloss over the tricky distinction between what's hardwired and what's learned, acknowledging that our current understanding of this boundary is pretty fuzzy. And that brings us to the end of this exploration. We've moved from viewing the nervous system as a passive recorder to seeing it as an active hierarchical controller deeply embedded within a living organism. We've seen how sensation and behavior are inextricably linked, how internal states and external stimuli constantly interact, and how this complex dance gives rise to our structured experience of the world. This sets the stage for digging deeper into the very structure of this mental order.